Okay, in this lecture we take a look at another important calculation. This is finding the potential at some point P in space due to a dipole. So I've already drawn the situation for us here on the board. Recall what a dipole looks like. We have a positive charge here and a negative charge here. The distance between the two charges is 2a. Okay, and then here's our point P in space, a distance r away from the dipole. However, specifically we're interested in calculating what happens if the distance r is very large compared to the distance 2a. So it's like we're trying to find a potential at some point in space due to the electric field associated with, say, a water molecule. And we just happen to be rather far from the water molecule. So that's what's being described here, for example, in this problem. Okay, now this is just a point P in space here, so then therefore to find that potential at that point, I'm going to find the potential due to each of the charges, of course, and then just add them together. Okay, now I'm not going to draw the following on the diagram. This distance right here that the positive charge is away from point P, I'm going to refer to that as R1. For the negative charge, its distance away from point P, I'm going to refer to that as R2. So then therefore, the potential at point P in space is going to be the following. First of all, for the positive charge, Q over 4 pi epsilon naught times R1. And then for the negative charge, so minus Q over 4 pi epsilon naught times R2. And now let me begin to draw R1 and R2, but I'm not going to draw them completely. Here's the beginnings of R1, for example. Here's the beginnings of R2. Remember that we're very far from the molecule. So if we're very far from the molecule, what that then means is the following. The three lines that I've drawn here are very close to being parallel to each other. Once again, this is the beginnings here of R1. This right here is the beginnings of R2. In addition to that, because we are very far from the molecule, R1 and R2 are about the same thing, and they're both about equal to R. So R1 and R2 are about the same thing, and they're about equal to R. Once again, all three of these lines here are very close to being parallel to each other as long as point P is very far away in space. Now, you look at this expression, you would then say to yourself, okay, well then the potential at point P is equal to 0 because these two terms just cancel each other out. Not quite, because R1 and R2 are about the same thing, yes, but they're not exactly the same thing. So then therefore, I'm going to start to combine the expressions together to illustrate how it's the distance r that's important. Okay, so let's go ahead and combine these two terms together by getting a common denominator between them. When I do, I obtain the following. Like so. Like so. Okay, now in the denominator, let's call R1 and R2 R. So then therefore, right here is an R squared, and right here is an R squared. And then in the numerator of the expression, I have R2 minus R1 multiplied by Q. Let me write that here. Minus R1 multiplied by Q, and then divided by the following denominator. Like so. Okay, now I'm going to lead you through a brief process that we do here in order to begin to write the numerator in terms of the dipole moment. Recall that the dipole moment is 2a times q. So let's take a look at the following portion of the diagram. What I'm going to do is I'm going to form a right triangle right here on the diagram that looks like this. Like so, where here's the angle theta from the diagram above. Here's the distance 2a between the positive charge and the negative charge. And then take a look at this side of the right triangle. This side of the right triangle, you'll notice, is the difference between R2 and R1. It's specifically R2 minus R1, which appears right here in the numerator of our expression. Now, in terms of the hypotenuse of this right triangle and the angle theta, notice that this side of the triangle, R2 minus R1, is 2a cosine theta. Like so. There's the 2a that we need to begin to describe the dipole moment. So now let's replace R2 minus R1 with 2a cosine theta. like so. And then right here is the dipole moment P. Recall that P, the dipole moment, is 2AQ. So the potential at point P in space is then therefore the following expression. We can actually write the numerator of the expression as a dot product. Notice that a cosine appears here, so mathematically, in terms of vector multiplication, it looks like a dot product. Recall that P is a vector. P, for example, is a vector, like so. The dipole moment goes from the negative side of the molecule to the positive side of the molecule. But then what is the other vector that we're taking the dot product with to give us the numerator of the expression? Well, it's a unit vector that specifically goes from this point on the diagram above towards the direction of point P in space, like so. This unit vector pointing in that direction is referred to as r hat, where right here is the angle between the two vectors. So then therefore the potential at point P in space due to a dipole is the dipole moment multiplied by the unit vector in that direction and then divided by this quantity here. Okay, you have to know how to do this derivation to arrive at this expression here. Every now and then it does pop up in the AP Physics C exam in some small manner.